In the Markov model, a number of health states are assumed together with the likelihood that a person transitions between the health state. Consider this very simple model where we have three health states. A person can be healthy, sick, or dead. Dead here is a so-called absorbing state. There is no way to leave this health state. When constructing a Markov model, it's important to consider that the more states that are included in the model, the less transparent the model will be due to the rapidly increasing complexity. In this model, we first need to establish that this is a chronic disease for which there is no cure. Thus, the possible paths or transition directions goes from healthy to sick, healthy to dead, and sick to dead. These are the only ways a person can move within the model. We now need to determine with what likelihood a person travels through the model. This type of information should preferably be obtained from large literature reviews, but also needs to be relevant for the context in which the model will be used. The likelihoods are called transitional probabilities. Let's assume that the transitional probability of falling sick, if healthy, is 30%. And the probability of dying, if healthy, is 5%. The probability of dying if sick is 20%. Remember that there are no other possible transitions in the model due to the chronic nature of the disease. But sometimes we do in a model also explicitly state the probability of remaining in a health state. So the probability of remaining in the healthy health state is 1 minus the probability of leaving, and in this case 0.65. The probability of remaining in the sick health state is 0.8, and the probability of remaining in dead health state is 1, as this was an absorbing health state. But we're going to disregard that kind of information for now, as that is already implicit in the model. We then need to set the length of the Markov cycle, i.e. the amount of time that needs to be spent in a health state before transition to another health state is possible. The cycle cannot be shorter than the minimum time to move to another health state, which might reflect disease progression or biological processes. However, this is often determined by the availability of data. In other words, the time period for which the transition probabilities are calculated in the original study. In our example, we will use a Markov cycle of 1 year for simplicity. We also need to consider the time horizon of the model, that is, over what time period it should run. This can be based on the expected number of remaining life years of the patient group, or the time period for which the current state of affairs is expected to remain constant, for example, before new treatments are developed. It is also possible to run the model until all persons have reached the absorbing state. In our example, let's assume for simplicity that the appropriate time horizon is 2 years, although this would be considered very short. We can now run our model. Let's consider 100 persons initially in the healthy state. After the first cycle, 5 persons will have died and 30 will have fallen sick. In the second cycle, around 20 of the remaining 65 persons in the healthy health state will fall sick, and while 3 will die. Of those 30 that are now in the sick health state from the first cycle, 6 of those are expected to die. This means that after 2 cycles, there will be 42 persons in the healthy health state, 44 in the sick health state, and 14 in the dead state. But this only models the disease progression. However, by adding costs and outcome to each of the health states, we can let the model accumulate the total cost as well as the total health benefit. This is broadly done as for any traditional economic evaluation, where we identify different cost components, we quantify value, and if needed, discount the cost. In our current example, there are no costs associated with being in the healthy state. Being sick is associated with cost due to health care. For example, aggregated cost for all treatments, including inpatient, outpatient, and primary care, pharmaceuticals, informal care, and lost productivity. Let's assign some values to these cost components. And this sums to 20,000. The state for dead also include cost in terms of lost productivity. Here we assign a cost value of 5,000. The benefits are measured as QALYs in this model, where being in the health state is associated with a health state weight of 0.8. QALY weight is equal to 0.8, while the weight, if you are sick, is 0.6. That is, if you're sick, you consider to be in 60% of full health. The weight for being in the dead absorbing state is 0. If we now run the model, we could accumulate the costs and the benefits. Those in the first cycle, we have 30 individuals that are sick or becoming sick. And each of those contribute with a cost of 20,000, which then gives us 30 times 20,000. But we also get cost for the dead health state. That was the lost productivity. And in the first round, we have 5 times 5,000, which gives us a total of 625,000. In the second cycle, the following cost will occur. We will have 44 individuals in the sick health state at a cost of 20,000. We will have 14 individuals in the dead state, and this will total to 950,000. However, these costs should obviously be discounted to the present value. And using a discount value of 3% will give us a present value of around 895,466. We can now sum the cost for both cycles, 625,000 plus 895,466, which gives us a total cost of 1,520,466. We can now do the same thing for the benefits. which we measure in QoLs. We multiply the number of persons in each health state with the associated health weight and the time in the health state. And here, for simplicity, we had chosen 1 year, which makes calculation of the QoL very simple. So we multiply the weight with 1 to get the QoL for one individual. So in the first cycle, we have in the healthy state, we have 65 individuals remaining times 0.8 times 1, because it's 1 year, gives us a total of 52 QoLs. In the sick, we have 30 individuals in a health state of 0.6 times 1 gives us a total of 18 QoLs. The dead health state, we have 5 individuals, but with 0 weight, gives us 0 QoLs. In the second cycle, the equivalent numbers are 42 times 0.8 gives us 34 QoLs. We have 44 in the sick health state, 0.6. It gives us 26 QoLs. And then for dead, we have 14 times 0. Again, 0. This gives us a total accumulated QoL of 130 over the 2 years. Now, I haven't discounted the QoLs in this case. So we have run the model for the base case scenario. And then this results in a total accumulated QoLs of 130 and a total cost of 1,520,466. Now let's say that we're developing a new drug that can treat symptoms and thereby improve quality of life while sick, but it has no impact on the transition probabilities. So instead of a health weight in the sick state of 0.6, we now model that the health weight is 0.7. So we had 0.6 and we changed that to 0.7. All other weights remain the same. The weight of being in healthy was 0.8 and the weight of being dead is 0. So if we redo the calculations using the same number of patients in the different states, since the drug doesn't affect disease progression, we get in the first cycle, for the healthy, we get 52 QoLs. For the sick, we get 21. It used to be 18 in the base case. And for dead, we get 0. And in the second, we get in the healthy health state 34 QoLs. In the sick health state, we get about 31. It used to be 26. And in the dead, we get 0. This totals to 138 QoL. It used to be 130. However, with the new drug, there is also an increase in cost. And this increase in cost occurs in the sick health state. So before we had a cost of 20,000 in the sick health state. And we now, due to the increased cost of pharmaceuticals, now add 21,000 for the cost in the sick health state. The cost in the healthy health state doesn't change, and it doesn't change in the dead health state, which was 5,000 due to the loss of productivity. Now, if we do this calculation and discount in the second cycle, we get a total cost of 1,591,940. This now allows us to calculate the ICER and the cost effectiveness ratio of the intervention, which is the cost of the intervention minus cost of in the base case divided by the outcome of the intervention minus the outcome of the base case. So the total cost of the intervention was 1,591,940 minus the cost of the base case, which we previously calculated to 1,520,466. We divide this by the outcome of in the intervention. We accumulated 138 QALYs. Subtract the outcome of the base case, which was 130 QALYs, and this gives us a ICER of around 8,934. Having built the model, we can now calculate the ICER for many different possible interventions by incorporating the effects and cost of the intervention and compare to the base case. We could, for example, if we have a new intervention that affects transition probabilities, we could change the likelihood of moving from sick to dead, for example. Or if we have a breakthrough and we get a cure, we could introduce a transition direction from sick to healthy with a certain probability and compare that to the situation as it is in the base case. The ICER that we have calculated is, of course, interpreted in the normal way, where we need to have an idea about what we are willing to pay as a society or healthcare sector for the outcome in question.